topic of this lesson is initial value of problem for ordinary differential equations. The topic is written here, and as usual, we start from the general problem statement. Here on the next slide, it will be some example, but before we consider this particular example, I want to discuss about initial value problems, maybe more simple, that is shown here in this applied problem. Well, what is initial value problems for ordinary differential equations? So the first question, what equation is called differential equation? Now I close my presentation and I write something on the board. Well, what equation is a differential equation? In previous lessons, we consider another type of equations like nonlinear equations or systems of linear equations when we discuss about least squares method. But what is a differential equation? Differential equation means that there is some unknown function It means that we have unknown function For example, I can denote it as y of x. X is example in some range from a to b. And we know that this function satisfies some equation written in the following form: y prime equals to f of x y. This is a general form of a first order differential equation. The function f in the right-hand side depends on the variable x and unknown function y. So here, y placed in both parts of this equation. In the left-hand side, we have derivative y prime. In the right-hand side, we have y. Y as a parameter, as argument of another function f. Let's consider some very, very simple examples of differential equations. For example, this equation y prime equals to some constant c. Y prime equals to c. What is the solution of this equation? What function satisfies this equation? What function satisfies this equation? Y prime equals to c, where c is some constant. Please, you can type your answers in chat. Y prime equals to C, where C is a constant. Y prime equals to C. Any ideas what function y we should take to satisfy this equation? Again, C is some constant. For simplicity, I can take C equals, for example, 2. Y prime equals 2. What is the function y? If y prime equals 2. You can answer using your microphones, you can type your answers in chat. The answer is very simple. The solution to this problem is very simple. Please type your answers. No ideas? What function we should take to satisfy this equation? What function y we should take to satisfy this equation? The answer is very simple. The answer to this equation is y equals 2x. If you compute the derivative of the function y, what is the derivative of 2x? Is 2. So we find that y prime equals 2. So the function y equals 2x is the solution to the equation y prime equals 2. Well, let me write this another example, another equation. Y prime equals x. Y prime equals x. And again, please think a few minutes and type your answers in chat. What is the solution to this equation? Well, x equals to 1? No. The second answer is correct. X is a parameter. X is the argument of the function. But the unknown here is y, is a function. And if you substitute here the value y equals to x squared over 2, derivative of y will be x. And you will have this solution. X squared over 2 is the correct solution to this problem. Well, next, very simple example. Suppose that we have this differential equation y prime equals to sinus x. Y prime equals to sinus x. What is the solution to this equation? Well, minus cosine, right? But minus cosine x is not complete answer. I explain you now. Y of x equals to minus cosine x is a correct but not complete answer. Because the complete answer can be written as I can write it in two different forms. For example, y of x equals to minus cosine x plus any constant. I can add any constant to y of x to get the solution. Why? Because the derivative of c of constant equals to 0. And when I add the constant, this function will satisfy this equation too. Or I can write this equation in this form. Y of x equals to minus k times cosine x. And in this case, the solution, this function will satisfy the first equation too. So in general, goodbye. Please send me this code, send me your solution. I'll check it and I'll give you my answer. Goodbye. Well, here we have two different forms of solution, but the main idea is that in general, if we didn't make any other suppositions, there are a lot of solutions, a lot of functions that satisfy this equation. Also here, let's consider first example. Y prime equals 2, y equals 2x plus constant. 2x plus c, because I can add any constant and this function will satisfy the equation. Well, the last example, the last case we consider, and after that we continue with my presentation. The most complex case, y prime equals to y. Y prime equals to y.
Charlie, we don't know what the doc said.
Turn. Y prime equals to y. What is their solution? The last question, y prime equals to y. What is the solution to this equation? Think for a minute, and after that we discuss about the solution. Y prime equals to y. Well, yes, the correct solution is written here in the chat, that y of x equals to e power x, e power x. But again, this answer is just a particular case, because in general, I can write that y of x equals to e power x times c multiplied some constant. And I can use any constant. 5, 6, 10. This function will also satisfy this equation. But how to find this constant? The main question, one of these questions, how to find this constant? And when we solve this problem theoretically, we should know some initial condition. For example, y of 0 equals to 1. So this is the complete problem statement. We know the differential equation, y prime equals to y, and in addition to this equation, we should know y of 0 equals to 1. Y of 0 equals to 1. And from this initial condition, we can find the constant. We can substitute these values here. I can write e power 0 times e equals to 1, and from this condition, c equals to 1. I can find the constant from the initial condition. Well, we discuss about general problem statement. Now let me show you. Not plus c. Yes, I can write e power x plus c, but I told you that I can write the solution in two forms, plus c or times c. But it's more simple to find the constant c when I write it in the form e power x times c. It's just for simplicity, but this form is more or less equivalent. Well, okay. Before we consider some particular example, maybe one more example of the differential equation. Here, I write you the examples of first order differential equation, but in general, it maybe we can consider so-called second order differential equation, something like this: y second derivative plus y first derivative equals to, or maybe plus some function equals to f of x to y, something like this. So here it's written the second derivative of the second order. These types of equations also can be considered and can be solved. Now let's come back to the presentation and let's consider this picture. This picture illustrates a swinging pendulum. And suppose that I want to find the position of this pendulum dependent on time. Suppose that I know the length of the pendulum, and the question is, what will be the angle theta between the current position of the pendulum and the vertical line? From the physics, we know that the motion of this swinging pendulum can be described by the second order differential equation. Second derivative d2 theta over dt square plus g over L sine of theta equals to 0. Again, L is the length of the pendulum, G is a constant, so-called gravitational constant of the Earth. Theta is the angle between the pendulum and the vertical line. And also, if we suppose that we know the position and the velocity of the initial point at the initial moment of time t0, then we have that is called initial value problem. For small values of the angle of theta, we can use approximation. Theta equals to sine of theta, approximately. This is true for small values of the angle, for small values of theta. And after that, this equation can be written in this simple form. In this simple form, d2 theta over dt square plus g over L theta equals to 0. This second problem, it can be solved by standard differential equation techniques. But this first problem, it cannot be solved. No methods, nobody knows the standard technique how to find the exact solution to this problem. So, any textbook of ordinary differential equations details a number of methods for finding exact solution. But in practice, just a few of the problems can be solved directly, can be solved exactly. And at the first part of the lecture, we consider the following problem: how to solve, how to find the approximate solution to the first order differential equation. dy over dx, or y prime, equals to f of xy. Subject to initial condition, y of a equals to y0. Later this lecture, or maybe next week, next lecture, we will have a deal with the extension of these methods to systems of first order differential equations. Well, the first question that we should answer what will be the approximation to the real solution? Because real solution to this problem is a function, is continuous function y of x that must satisfy this condition and satisfy this initial condition, this equation and this initial condition. So in theory, the exact solution is a function, a known continuous function. And in practice, we rarely expect to obtain the solution directly, just as a formula given y of x. Like in our examples, when we find the solution in just as a formula, y of x equals to e power x, or y of x equals to x squared over 2. It's just extremely simple examples. But usually, we construct a table of a function values. And this table of these values we consider as approximation to the values of real unknown function. And here we will use notation yi to express the computed approximate value of the real function value y of x at the point I. Y of xi is a notation for the exact solution at the point xi. And if we have such table, we can construct a function y of x that approximates this data. The numerical methods for solving such approximation problem we considered on previous lessons. Lagrange interpolating polynomial when n is small, or least squares method and least squares polynomial when n is large. So we can use different methods for approximating a function when we know this table of the values. Well, I repeat it again and I write it on a board. That in general case, in theory, we have some exact solution. We have some exact solution to this problem. Of course, in theory, there exists an exact solution y of x in the form of a continuous differentiable function that satisfies this equation and that satisfies the initial condition. So, in theory, exists y of x, but in practice, we cannot find y of x, but we can find the table of approximate solution. We can build a grid with the nodes x, xi, starting from the known point x0 with the step h, x0, x1, x2, and so on, xn, where the difference between these points xi minus xi minus 1 equals to h. The point axis, the axis we can build exactly, but why I? We don't know the values of yi. We know only y0. From this initial condition, we know the value of y0 and y1, y2, y3, and so on. These values we are going to find. This is the goal, to find y1, y2, y3, and so on. Okay, I come back to the presentation. Well, let's consider the initial value problem. Y prime equals to f of xy, y of x0 equals to y0, where f is a function of two variables. We know this function. In some cases, this function may be very simple, just x or just y, or maybe y plus x or x times y, something like this. And x0, y0 is a single given point through which the solution curve should pass. To illustrate the main idea, the main approach, let's consider a concrete example. Suppose that y of x equals to cosine x minus sinus y plus x squared. This is an equation. Y of minus 1 equals to 3. This is the initial condition. The heart of the procedure is a Taylor series for x, which we can write in this form. Y of x plus h equals to y of x plus h y prime plus h squared over 2y second derivative plus h power 3 over 6 third derivative, and so on, the terms of h power 4 and larger. This is a standard Taylor series for x that we use in many methods. The derivatives appearing here can be obtained from the differential equation. The first derivative, we know it directly. The first derivative is written here. The second derivative we can compute as a first derivative of first derivative. third derivative, derivative of power 3, we can compute as the first derivative of the second derivative, and so on. Suppose that we decide to use only terms up to and including h power 3 in the formula. The terms that we have not included start with the term h power 4, and so on, h power 5, h power 6, and they constitute collectively so-called truncation error inherent in our procedure. The resulting numerical method is said to be of order 3. It means the order of the Taylor series is n if terms up to and including h power n are used in this formula. We can perform various substitutions to obtain formulas for hx second derivative, third derivative, and so on. At each step, the local truncation error is of order h power 4, since we have not included terms involving h power 4 and h power 5 from the Taylor series. Thus, when h tends to 0, the behavior of the local errors should be similar to some constant times h power 4. Unfortunately, we do not know the constant c, but we know that this term equals to c times h power 4. If h equals to 10 power minus 2, h power 4 will be 10 power minus 8. So, with a high probability, the error in such step should be roughly of the magnitude 10 power minus 8. But after several hundred steps, these small errors could accumulate and spoil the numerical solution. At each step, except the first, the estimate yk of y of x of xk already contains errors, and further computations continue to add these errors. The local truncation error is the error made in one step when we replace the infinite series of a finite one. In our particular example, we replace the infinite Taylor series for y of x plus h by a partial sum. So we truncate the terms of order h power 4 and larger. And the accumulation of these many local truncation errors gives rise to the so-called global truncation error. And there is a rule that if the local truncation errors are of order h power n plus 1, then the global truncation error must be of order h power n, because the number of steps necessary to reach an arbitrary point x is approximately x minus x0 over h. This is a very, very general approach, but this approach, it's hard to implement because in general case, we don't know the high order derivatives of y. We know only the first order derivative, y prime, from the differential equation. In this case, the Taylor series method is called Euler's method. So, if we take Taylor series method with n equals to 1, it means that we take only the first power of h power 1. In this case, the method called Euler method. And the formula looks like this. Y of x plus h equals to y of x plus h times f of xi yi. This formula has the obvious advantage of not requiring any differentiation of f of xy. And as far as we take only h power 1, the local truncation error of Euler method is of order h power 2. And then the global truncation error must be of order h. So the Euler method is a first order method. And to interpret the Euler's method geometrically, note that when yi is a close approximation to y of x, this assumption that the problem is well posed implies that f of xi approximately equals to y prime of x equals to f of xi y of xi. This is the geometrical interpretation of the Euler's method. Suppose that this is the initial point A that equals to x0, or in this example, it denoted as a t0. This is a curve of the function, a known function y of t that passes through this point. The derivative y prime at the point A can be considered as a slope of the tangent line to this curve. We can draw this tangent line, the line with the slope of f of a alpha that equals to y prime of a. Then we can take the next point t1 and select the next point at this line. And we can consider this value as the first approximation to the value of y of t1. Then we take this point as initial point, draw a line from this point, and take the point of this line at the point T1, and so on. So step by step, we build piecewise linear approximation of the unknown function y of t. If we select the step significantly small, this piecewise linear approximation will be close to this unknown function. Well, one step of Euler method is shown in the left figure, and a series of steps is shown on the right figure. Okay, let me come back to this formula, the formula of Euler method. And now let's try to apply, to understand how it works. Please fix this formula, or write this formula on your pen and paper, or if you forget this formula, you can just type in Google. If you type Euler's method for solving differential equation, Euler method, for differential equation, I think the first link to Wikipedia, more or less the same picture, the picture that illustrates the piecewise linear function that we consider as approximation to this unknown function. And also you can find the general formula of this method. So all the topics you can easy to find in Wikipedia. Well, now I ask you to apply this method and to find a few first few values that approximates the real solution. Let's consider the last problem. The problem from our last example. Y prime equals to y, and y of 0 equals to 1. Y prime equals to y of 0 equals to y. You already told me the exact solution. Y of x equals to e power x. But suppose we don't know how to find this exact solution, but we want to apply the Euler method to this problem with step h equal to 0.1. I ask you to find a few points, the first few points, to fill this table with these initial values. What is x0? X0 is 0. What is y0? Y0 is 1. What is x1? As far as h is 0.1, x1 will be 0.1. Now I ask you to substitute these values into the formula and find y1. What will be the value of y1? please find the first value of y1. Find this first value and type your answers in chat. Well, did you find the first point or not? Well, I'll give you a few minutes more to find this first value. I write you on the board the problem statement, and I ask you to find the first point using Euler's method. Well, no ideas how to solve this problem. Well, I can write the solution on a board. I think you can see it, or I can type it. Or, but I think you will see the board. According to the Euler's method, y plus 1, the value of y at the next point, equals to the value of y plus h times f of x I y I. What is f of x I y I in our example? It's the right-hand side of the equation. This y. F of x I y I in our particular case equals to y. What is h? H is 0.1. The value of h is 0.1. We should start from I equals to 0. When we write for I equals to 0, I can write that y1 equals to y0 plus h times f of x0 y0. But y0 in our case, f of x I y I is y times y0. This is a very, very simple formula. And for these particular values, we will have y0 is 1 plus h 0.1 times 1, and we have 1.1. 1.1 as the value for y1 equals to 1.1. What we should do next? We should compute y2. y2 we should compute using y1. So the next point we compute using previous point. y2 equals to y1 plus h times y1. Again, we have this very simple formula because in our case, the right-hand side is also very simple. And we have 1.1.
Я рубильник не выключаю, да?
Не
Сейчас я закрою, ключ.
Да, спасибо. 1.1 plus 0.1 times 1.1. and we have 1.21. And so on. And so on. Y3. Y3 we can find as Y2 plus H times Y2. You should substitute this value of Y2, H, and compute the value of Y3. And so on, step by step, on this way, we can fill this table and we can find the approximate solution to the unknown function. Well, and this method we can apply for any right-hand side, for any function. This method is very easy to implement in the form of the program C++. To understand how it works, I ask you to solve this exercise. Exercise 1. Here you may find two simple equations. Y prime equals to 1 plus x minus y in square. X between 2 and 3. Y of 2 equals to 1. This is the first equation. The second equation, y prime equals to 1 plus y over x. 1, x is between 1 and 2. Very important question. What will be the error of our computations? What is error? Error is the difference between approximation and the real solution. How to find this error? Only numerically. Only numerically. For example, in our case, let me start calculator. Just as a simple example, I show you it's in calculator. For example, let's consider the point 0.1. No. Yeah. Boom, boom. Where is exponential function? Zero 0.1. No. Okay. E power x, right? This is E. Let's raise in the power 0.1, right? 0.1. Well, this is a exact value. 1.1, 0.5, 1.7, and so on. This is the exact value. What we get by Euler's method? We get 1.1 at the first point. So this is a first order approximation. 1.1 at the first point. Well, what we get on the second point? Let's compute the real value. Let's compute the real value e power 0.2. This is the value at the second step. At the value 0.2. 1.2214. But what we get by Euler method? By Euler method, we get 1.21. Again, this value 1.21 is very close to this real value. We can compute an error. This value minus 1.21. This is the error, 0.01. This is the error. So, in your task, you can compute the error, because here, exercise 2 is written the exact solution to these problems. This and this, the exact solutions. Well, I ask you to apply the Euler method to find the solution, approximate solution with a step 0.25 to these problems, and after that, find the error. Find the error as a difference between the real value and approximation. Well, that's all for this lesson. Next, again, I said again that next week I will be busy. That's why we will meet week after week. We continue our discussion about the differential equations, and we discuss about high order methods for solving differential equations. And I show you the program, how we can implement Euler method and high order methods in the form of a C++ code. I show you the program that solves some differential equation. Today, later, I will send you the video file. I will send you the presentation.
Okay, thank you, sir.
Do you have any questions?
I don't have anything.
If you don't have any questions, let me stop recording.